I'm very privileged to welcome folks to the second episode of iFyber's Research Development and Implementation webinar series. This time we're going to be talking about liquid chromatography-Mass Spectrometry, powering advanced analytical applications into the future. Our speaker today is Gary Schultz. Gary has 30-odd years of experience with LC-MS. He's a native Wisconsinite, PhD from Michigan State University, and a lot of experience in both the systems side and the services side of LC-MS. Over the course of Gary's career, he had a 17-year stint with a company, started out as ABS, grew into the company called Advion, and this was at the forefront of doing small molecule identification for drug development. Advion grew into being acquired by Quintiles, and over 17 years, Gary was there working and leading efforts in that company, which eventually was turned into Q Squared and is now IQVIA. Gary spent kind of the next 10-odd years as a consultant working more on the system side with the bigger LC-MS companies, developing new technologies and new systems to do what we're going to talk about today. So welcome everyone who's kind of joining in. The format for today is about 30 minutes of remarks by Gary, and then a 20-minute discussion session where we could kind of go through questions and talk through some things. Please keep your microphones muted, and if you have any questions, just type them into the chat in real time, and we can either answer them while we're going through, if it's kind of a pressing matter, or we could kind of handle them in the discussion at the end. We're going to record the webinar for folks that weren't able to make it today, so that they can see it later. So be aware of that. And without further ado, I'd like to turn it over to Gary.
Thank you, Greg. So again, just going to be giving it a little overview of liquid chromatography-mass spectrometry and how we use this technology to power some of the research that we do here at iFyber. In the last 10 years, there's been significant advancements in system performance for UHPLC integrated with mass spectrometry. And particularly with UHPLC, with the development of pumps that can operate up to pressures of exceeding 1500 bar pressure. What that enables us to do is to use smaller and smaller particles, which improve separation efficiency, and I'll get into that in some of the subsequent slides, the details of that. But the real benefit in addition to that is really the system integration, integrating LC systems directly with electrospray mass spectrometry systems. It's really through that close integration that overall system performance has improved dramatically over the past 10 years, and want to highlight some of those benefits in our talk today. The LC system itself incorporates temperature-controlled column compartments and also temperature-controlled sample compartments that enable us to overall improve retention time stability and also sample stability throughout the course of these hours-long runs. The other advantage of recently developed is the ability to do multi-dimensional LC, combining 2 or more stationary phases in series in order to further enhance the separation selectivity of a method. And really, LC, I'll get into this in another subsequent slide, but it does significant advantages with terms of the chemistries that are now available with HPLC technology, really able to separate molecules based on their physical properties, such as molecular size, hydrophobicity, hydrophilicity, charge, and with the use of antibody columns, antibody interaction. I'm also going to get into some details around different modes of electrical ionization. This is a means to convert gas phase, convert liquids into gas phase ions. And there are different flow regimes which affect the performance of electrospray. And then I'll also summarize and highlight a few of the different types of mass spectrometers and their performance benefits for various applications. Well, one of the main reasons why pumping technology has been developed to work at higher pressures is to be able to take advantage of improvements in separation efficiency. By reducing particle size, we can increase the number of theoretical plates that are available and achieve an equivalent separation in a shorter period of time. So historically, particles were typically in the 5-micron size. And by going now to these smaller particles, we can increase the separation efficiency by about a factor of 3. And what that means is that you can achieve the same separation in 1/3 the time that it used to take traditionally. The challenge there is that you require about a 9-fold improvement in pressure performance, and that's what the latest technology has achieved over the past 10 years. So that gives us better separation efficiencies, also sharpens chromatographic peaks, which improves signal to noise when coupling these technologies with quantitative detectors such as mass spectrometry. So there's of course benefits and trade-offs when choosing which column diameter to use. So in addition to shrinking particle size, we also have the opportunity to decrease the column diameter. And these circles just physically represent the relative scale of a traditional 4.6 millimeter HPLC column that typically operates around a milliliter per minute to, say, a column that operates with a 1 millimeter diameter at 50 microliters per minute. The benefits of these larger diameter columns is if you don't have a method that has a high sensitivity requirement, we have a higher loading capacity with the larger diameter columns, and depending on the degree of method development required, the smaller the column diameter, the more method development is required in order to simplify and clean up analytes from background matrix effects. And one thing that is the case is that by going from 4.6 millimeter down to, say, a 75 micron ID column, there's a dramatic reduction in flow rate, but that with that comes efficiencies, both in separation efficiency and also ionization efficiency. So in the end, what we don't want to do is choose the column diameter and to match the system requirements for any particular method. Where if you have a lot of sample and moderate sensitivity or low sensitivity requirements, we can get away with using 2.1 to 4.6 millimeter column. But if you have a limited amount of sample or require trace sensitivity, we have to migrate toward capillary and nano-LC columns. And as we do that, the complexity of the method increases significantly. And that method complexity can involve multidimensional cleanups before we reach the LC system, or multidimensional LC systems in order to fractionate and clean up the sample as part of the LC-MS analysis itself. And really, the goal here is that we want to match the analytical performance to the sensitivity required to meet your needs. From a separation point of view, liquid chromatography is an analytical method that separates component mixtures through partitioning between a stationary phase and a mobile phase. And the stationary phase can be modified and chosen to select the separation mode based on the most unique physical characteristic about your analytes. If you're trying to separate polymers or large proteins, size exclusion chromatography is a really good approach to do that. The stationary phase is typically porous beads, either silica or polymer based, and it does simply separate molecules based on their size. And reverse phase chromatography is probably the most commonly used stationary phase. Typically used for small molecules and peptides. And the separation is based on hydrophobicity. Typically run a solvent gradient that will slowly change from high aqueous to high organic. And as the analytes are, the more hydrophilic analytes will elute earlier in a gradient, the hydrophobic analytes will elute later in the gradient. And it's just a matter of changing the composition of the mobile phase in order to affect that partitioning coefficient between the mobile and stationary phases for each particular analyte. It has strong applications in small molecule and drug analysis and peptide analysis from bottom-up proteomics. Hydrophilic interaction is commonly used for analytes that are very hydrophilic. Compounds that are very little retained with a reverse phase hydrophobic stationary phase. So for polar compounds, carbohydrates and polar metabolites are commonly used with hydrophilic interaction chromatography. We can also separate analytes based on their charge, and we use ion exchange chromatography to do that. And also we can make special antibody columns to see if an antibody to target any specific peptide or protein that's of interest to you. We can bind those antibodies to particles and then put those particles inside of column bodies and then use those to selectively extract and isolate your peptide or protein from a complex mixture. Oftentimes, these different modalities are used in series in combination in order to provide an orthogonal means of separation in a two-dimensional LC-MS experiment. And choosing these phases either singularly or in combination provides the type of selectivity required in order to separate your target analytes from the other components which are in that sample. So just to look quickly at the system configuration, the LC system is the pump and autosampler column oven. And then the electric spray interface is the means to taking a liquid-based sample coming from an LC system and atomizing that sample in front of an ion source, so a mass spectrometer that allows the ions to pass into the mass analyzer system. And electrospray itself is involves the application of a high voltage to a tapered, typically metal needle, but as we go to lower flow rates, we typically use capillary, pulled capillary glass emitters for the emitter. And by applying high voltage to this sprayer in combination with some sheath gas and nebulizing gas, we can form an electric field between this emitter and the MS inlet and cause charged droplets to form as part of that process. The droplets themselves need to evaporate to leave a charge residue on our analytes, and we do that through the assistance of gas and heat in order to help evaporate those droplets. So electrospray itself, ionization is considered a soft ionization technique. In positive ion electrospray ionization, it typically will attach a proton to the molecule. And so, of course, mass spectrometers detect mass to charge species. And so by placing those protons onto these molecules, typically we'll measure the molecular ion. So it'd be the molecular weight plus one proton for a singly charged ion. And so this involves, again, applying high voltage to that liquid stream, and through charge repulsion can create a fine aerosol of charged droplets. At higher flow rates, we use nebulizing gas and heat to assist it in both droplet formation and droplet evaporation. It's once those droplets shrink to a small size that they leads to gas phase ions that can be sampled then into the vacuum system of the mass spectrometer. ESI is widely used for the analysis of biomolecules such as proteins and peptides and nucleic acids. There's really multiple regimes of ionization, electrospray ionization, that are terms that should be maybe explained. Ion spray is a term that has been used to describe electrospray with flow rates from higher than 100 microliters per minute. And microspray is used for these intermediate flow rates, typically used with a 1 millimeter diameter column, LC column. Capillary ESI is typically used with a 0.3 millimeter ID column, and nano ESI is more typically used for 75 micron ID column. As you go to lower flow rates, we can improve ionization efficiency, and so not only do you benefit from a concentration benefit with the chromatography, you also can benefit from improvements in ionization efficiency to enhance overall sensitivity for the method. I just wanted to show briefly, in case you're unfamiliar with how mass spectrometers are configured, and I'm just going to show as an example a triple quadrupole mass spectrometer. So once the ions are formed in the ion source and sampled into the vacuum system, we use in a triple quadrupole, there are three different quadrupoles. The first one can be used to select the precursor ion for your target molecule. So as I said, for singly charged ions, we'll add one proton to the molecular mass and end up with a mass to charge of 651 in this example. If you have a molecule that can form attach two protons, then you will end up with a mass to charge of 454.5. And what we can then do is select just these two ions out of all the ions that are entering the mass spectrometer, and then fragment those two ions, and then measure specific targeted product ions for these two species. And that's essentially how a triple quadrupole works. We choose which ions pass through this first filter, fragment those ions, and then measure the product ions selectively. And these quadrupoles can switch from one selection to another in the course of around 2 milliseconds in today's systems, allowing for hundreds of SRM selected reaction monitoring experiments to take place every second. And for a time of flight instrument, they also typically have a quadrupole mass filter on the front end, and then simply replace this third quadrupole with either time of flight or, say, an Orbitrap in order to operate with these various mass spectrometry technologies that are in use today. For electrospray ionization on large molecules, so what happens is that the larger the molecule, the more proton sites are typically available in order to add protons during the electrospray process. And that's a really huge advantage when trying to analyze large molecules such as large peptides and proteins. In that the mass range of these analyzers does have a limit, particularly with quadrupoles. And so this benefit of electrospray ionization is that these large molecules, which in this case is example of human insulin. Human insulin will form a protonated molecule up here, but also forms the most abundant ion is the M+4. So we add four protons to this species, and then it causes the mass to charge to fall down to 1452. And you can zoom in on this peak right here, and this is what the insert shows. is that when you use the high-resolution mass spectrometer, you can start to resolve all these different charge states and then the isomers that fall within this peak. So again, earlier I had talked a little bit about the benefits of reducing column diameter, and that's sort of shown graphically here. But by going to smaller diameter columns, we also not only just gain in separation efficiency, we also enhance this concentration sensitivity. And sensitivity increases proportional to the inverse of the diameter squared for the column. So if we had an assay that was running on a 2.1 millimeter column and we needed to have improved the sensitivity, say by a factor of 200, we could go to about 100 micron AD column. But if we go all the way down to a 75 micron ID column, we could get almost a 800-fold improvement in sensitivity just by changing the column diameter. There are some caveats to this because it's not completely, we don't really gain this full theoretical sensitivity because of matrix effects and other issues related to that. But theoretically, there's a significant fold gain in sensitivity that is available. And in order to gain this sensitivity, we really need to optimize the method itself in order to achieve as much of this as possible. And so here's an example for human insulin. I have an assay that I ran for human insulin on a 2.1 millimeter column and measured the peak area for insulin. And then I ran those same extracts on a 0.3 millimeter column operating at 10 microliters per minute. Theoretically, we should have achieved about a factor 49 in terms of sensitivity gain. Experimentally, we only achieved a factor 24. And we also ran these samples on a 75 micron ID column. And again, theoretically supposed to gain approximately 800-fold gain, but experimentally we only got about a 200-fold gain of sensitivity. So this difference between these numbers is related to co-elution of other components and their competition for the ionization and for those protons that take place during the gas phase production of these ions. And so what we can do to improve upon this matrix effect is to use selective extraction, preferably an extraction modality that's orthogonal to the separation. So if we're using a C18 separation phase for the LCMS, we want to use, say, an ion exchange or a size exclusion or affinity-based separation at the wet bench. So one of the areas of interest in today is the analysis of short chain fatty acids. And these fatty acids are typically less than 6 carbons in length. And they exist within the gut microbiota and via dietary fermentation within our digestive system. And they play a key role in metabolic health, both in terms of energy sources, and they also strengthen our GI gut barrier strength and also reduce inflammation. The short-chain fatty acids that are produced in our system contribute to some of our calories for the day and play a role in regulating immunity. And there's lots of research into this gut-brain axis influenced mood and cognition through some signaling pathways. Short-chain fatty acids are also playing a role in lowering blood pressure and improving blood pressure profiles and system inflammation, and that they're important in research related to cancer. because there are some indications that butyrate may inhibit some tumor growth, and also protect against non-alcoholic fatty liver disease. And so these short-chain fatty acids have an emerging role in metabolic disorders and potential therapeutic potential. The separation of these short-chain fatty acids by LC-MS, an example that is shown here, where there are acetic acid peak will elute first, and then propionic acid second, and butyric acid third. There's 3 peaks here. The top chromatogram is used for quantifying each of these components, where these other 2 chromatograms from this triple quadruple measurement are used as sort of qualifier ions to confirm that there's no co-eluting interferences within each of these unique signals for each of these 3 analytes. They're highly polar species, very low molecular weight, some volatility. So we've got to take that all in the mind as we develop these methods. But they're present both in plasma and feces and lots of other bodily fluids. Benefit of these is that they're non-invasive biomarkers and can be used for personalized medicine. And there's multiple ways that these have been separated and analyzed by LC-MS, including derivatization or not derivatizing these analytes, depending on the needs for the sensitivity and selectivity for the method. On a larger molecule side, immunoaffinity mass spectrometry is typically used in 3 different modes, and is used in combination with mass spectrometry. We can capture target proteins at the protein level by using an affinity antibody at the protein. And we can either do that in solution at the bench, or we can do that in combination with a column-based affinity system. And so that we can either analyze that protein directly with LC-MS after it's captured to get intact molecular weight information and some structural information through MSMS on the protein level, or we can take that protein and digest it to the peptide level and then measure the peptide of a target protein. So long as that peptide gives us selectivity and specificity, that's a very common method of quantifying proteins today. And with that modality, we typically will add after we capture that protein, we'll introduce a peptide that will then go through the digestion process along with the protein, and therefore capture any variation in digestion efficiency from one sample to the next. We can combine together affinity capture at the protein level, add a stable label peptide prior to digestion, and then actually capture both of these, the peptide derived from the protein and the peptide heavy label derived from this digestion for the internal standard, and then combining 2 affinity techniques together in order to enhance the selectivity even further. And so these workflows, zooming in on the LC-MS part of it, if we capture a protein, we can either do that offline and then analyze that protein directly through the LC-MS. These analyses are typically done with high-resolution mass spectrometers, such as time of flight and the Orbitrap systems. Or we can capture that protein in a column-based modality. So we can use affinity protein capture in a column combined with a second column, which would typically reverse phase or size exclusion in this case, prior to the MS. Or we can capture that protein and digest it in order to then capture the peptide prior to the LC-MS analysis. So which mode you implement depends on sensitivity and selectivity, of, the method itself. So what does that look like experimentally? Here's an example of a paper from Hendrik Neupert out of Pfizer. And what this method did was to capture a beta NGF, nerve growth factor protein, with an antibody in the 96 well plates. We then combined the assay with magnetic beads that were streptavidin coated. We had biotinylated antibody to the protein. And after we capture that complex, we then can elute, wash the beads and elute this protein, and then go through a 16-step extraction procedure to then do our best to isolate this peptide or this protein. We then digest this captured protein with a heavy labeled peptide for the internal standard, and then analyze that with LC-MS. And this work involved so what I show here is, so this is a digestion at the protein level to a peptide, and this shows the peptide signal when we also incorporated the use of an antipeptide column in combination for the LC-MS. So the LC-MS actually had three columns. It's the antipeptide column and then a trapping column in order to concentrate the peptide that we captured with the antipeptide, and then to further elute that trap column to a nano LC column in order to achieve a 7 picogram per mil LLQ for this particular biomarker. And what I'm showing here on the left panel is the signal to noise ratio obtained when using the antipeptide column, and on the right is showing the same samples injected without use of the antipeptide column. So if we just took the protein and digested it off of the bead, this is the result we would get. And so we can see we get an 18-fold improvement in signal to noise by simplifying the sample that actually reaches the MS interface. This particular method was enable us to analyze over 19,000 clinical samples as part of high throughput support for a clinical program. So I hope that this presentation was able to give you a little bit of insights into what we're capable of achieving today with LC-MS. The future of ultra-high performance liquid chromatography coupled with mass spectrometry is really going to be enhanced and have significant contributions in the field of proteomics, metabolomics, and environmental analysis. The future is continuing to improve upon enhanced sensitivity and resolution through the use of these sub-2 micron particles. And also there's coarse shell particles that I didn't talk about today, but are also playing a role in improving overall chromatographic performance. And mass spectrometry systems are being able to scan more quickly at high resolution and provide more complex methods of fragmentation that enable us to generate a significant amount of data all in real time as peaks elute off of these columns. There's a large push today in the use of miniaturization, both in terms of the column diameter and the fluidics, but also through the integration of these systems in order to maximize overall system performance. And by pulling all these things together, it leads to a higher separation efficiency that can be achieved. More and more, there's automation both at the sample preparation at the bench leading up to VMS, but also there's lots of systems that are being commercialized today that incorporate automation and of sample throughput, of sample preparation and analysis all into one integrated system. And that's some of the new technology that's emerging today. Of course, with all these systems that scan at high resolution and with faster and faster scan speeds, we're generating an enormous amount of data. And that data becomes the bottleneck now for analyzing that data to make sense of what we're seeing. And so there's a lot of developments today, again, in artificial intelligence and machine learning, in order to go through this data, in order to help identify the small molecular changes that take place in these untargeted analyses. One thing I didn't mention, but it's also an emerging component of the mass spectrometer, is this methodology of ion mobility. It adds within the mass spectrometer itself adds an orthogonal means of separation based on isomeric differences, and so the different isomers being able to separate based on the ions interaction within a low pressure, moderate pressure region within the mass spectrometer. This ion mobility has actually played a significant role in proteomics and able to separate singly and doubly charged and triply charged ions, which enhances the proteomic findings, and also plays a role in us being able to screen complex lipid samples. The lipids can be, 10,000 or so lipids within any given sample, and by combining ion mobility with LC-MS, we're able to provide an enhanced separation of lipids through this extra dimension of gas phase separation. I want to leave this slide up just for a second. There's a number of papers here. I didn't get into the details of how we are able to quantify endogenous metabolites, but this paper here goes into some details as to how this is achieved. It does take a little bit of effort in terms of the type of method approach, in terms of the sample extraction, plays a significant role in the quantitative nature of this work. And this paper does a really nice job of summarizing that. This middle paper here is open sourced, so you can click this link, you'll be able to get access to that paper directly. And this just highlights the sort of the state of the art just a few years ago around protein biomarker quantification in combination with the immunoaffinity liquid chromatography. And then this last paper was the one where we published the work around the large-scale implementation of the sequential protein and peptide capture for beta nerve growth factor. So thank you for joining us today. We hope this presentation has provided an introduction to liquid chromatography-mass spectrometry and how it can help answer important questions to your business. And please reach out to us at iFyber to explore how we can assist your business in leveraging this technology to achieve your goals. Thank you.
Thanks, Gary. Appreciate it. Are there any questions from the audience? I know I have a couple, but I'm curious whether anyone on the call has a question for Gary. I mean, just from a high level, from my standpoint, somebody like me, this technology is somewhat intimidating. It seems extremely powerful. You could do a lot of really amazing stuff with it, but it's opaque to me on how you would apply it to different research questions that we or our customers might have. And I wonder, Gary, if you could, take a particular slide that stands out to me is that insulin slide, where you have kind of one peak and then there's the inset that has a bunch of little peaks that combine to make that one peak. If you go back to that, I guess just my question on a high level is, what are the practical applications of that, and what that would mean to a researcher who's looking at a sample and trying to understand what's going on there? Could you speak any more to just what is really happening here?
Just within this spectrum itself?
Yeah, and what a researcher could do with the information that is provided by the spectrum.
Well, typically, typically what we can do is we have software that can deconvolve this multi-charge spectrum to create a mass, sort of a mass spectrum of just the mass itself. And so if you analyze this on an Orbitrap instrument, for example, or a time of flight instrument with a resolution of around 100,000, what you can do is deconvolve these multi-charged ions, because it's just simple math to convert these back to the nominal mass.
Okay.
And then you can actually measure this nominal mass to within just a couple of ppm of mass accuracy. So to be able to actually measure insulin, to it's the third or fourth decimal point on the mass is quite remarkable. And so
okay, so it's a precision thing that you can get an extremely high level of precision if you break it down into these discrete peaks.
So all the software, I mean, this is an outcome of electrical ionization, this multiple charging. And what we typically would do, like in this example, I guess I don't show the I don't show the chromatograms for that, but the data example was an SRM, a quadrupole based assay. We isolated the 1452, fragmented that, and collected a specific product ion of that fragmentation in order to measure how the sensitivity increased with scaling the column diameter.
Okay.
But this is just this is a common thing that happens for large molecules. It's a great benefit because it drops these mass to charges within a reasonable range for the mass spectrometer to handle. And so it's just it's nothing too remarkable.
Okay. All right. Any other questions for Gary? I'm curious. You'd mentioned these orthogonal methods on the liquid chromatography, where you would kind of put two columns in series.
Yeah.
Can you explain a little more on that and how you come to the decision to use a method like that and execute on it?
The main reason and the beta NGF, the last example, was sort of one of the best examples is that the client had a goal of achieving this very, single-digit picogram per mil measurement on a 13.5 kilodalton protein, and to do that in a high throughput environment. And the only way that we could achieve that performance was to use an affinity capture at the protein level and affinity capture at the peptide level in order to achieve that performance. So really the main driver to using multi-dimensional chromatography in combination with mass spectrometry is the assay sensitivity requirements.
Okay.
And in order to get sensitivity, you have to you have to remove the complexity of the sample matrix itself. We do that with sample cleanups at the bench using solid phase extraction modalities, or and typically the separation at the bench just there's all these different phases in chromatography. These phases all exist in terms of solid phase extraction modalities too. So oftentimes for the most part, we use reverse phase chromatography combined with mass spectrometry. But what we'll do to separate to actually clean up those samples, we'll use an ion exchange cartridge in the wet lab, and we'll separate the target analytes using ion exchange, or we use a helic-based solid phase extraction modality, and then use that in combination with reverse phase or size exclusion. So essentially, what we do in order to extract, have a targeted extraction of analytes of interest from your matrix, you combine one of these different modes at the wet bench, and then in combination with orthogonal method of separation with the LCMS. Sometimes you need to do affinity capture at the protein level, like we did with the beads, and then combine that with also affinity at the peptide, and also with two different reverse phase modalities. So it's really driven by the needs of any particular method.
So the needs that the client has for precision and sensitivity, and then also what the matrix is.
Yeah. So sensitivity and speed and selectivity is what drives all the decision making around this, this platform.
Gotcha.
But the benefit is that we have all these tools available to us today in order to target specific analytes. Be them lipids or polar metabolites or proteins or anything else.
And that's what I hope people kind of come away from today, is that there's got a lot of sunshine. That there are a lot of options available to solve the problems that you guys might have, and taking a few minutes to sit down with Gary and members of our team to talk through what is possible might be worth it, because things have evolved pretty rapidly since these techniques became available 30 years ago. It's a whole different world. So any other questions for our expert Gary? Well, I really do appreciate everyone sitting in today. Like I said, this was the second version of iFyber's webinar series. We're going to continue to have these every month and a half or so. We've got some future topics that we're looking at: advanced tissue modeling, control of biofilms. There's a potential for a customer of ours to talk about resorbable devices and their development. Continuation of our inaugural webinar and talking about simulation and training. Talk about viral inactivation. We've got a number of different kind of wider ranging topics that have kind of a research and development bent to them, but also how they would be implemented in a production environment or in more manufacturing for these medical devices, drugs, and biologics. I do want to mention also that our team is going to be out and about in the next coming weeks. So if any of you are going to be at the MHSRS meeting, which is a military health symposium in Florida, we'll have a team member attending that. That's next week. We're going to be at the Society for Advanced Wound Care the first week in September in Las Vegas. And we'll have a team member at the European Society for Biomaterials in Torino, Italy, the second week of September. So we've got East Coast, West Coast of the US, Europe covered in the next 6 weeks or so. And if there's any desire to meet with any of our team in person, please reach out to me directly. With that, I'd like to thank you all again for your time and attention. Thank Gary Schultz so much for his expertise and for sharing this with us today. And we will see you next time.